Hi there! Today's video will explain in detail how we can reduce questions in engineering applications, specifically in robotics control, to optimization and equation solving. We will start with an explicit such problem and guide you step by step on how to reduce them to optimization and equation solving. Before that, let's go over some general concepts. Problems in engineering often involve functions and their derivatives on an interval from A to B. A point t within A and B usually represents time. We often deal with functions like y of t and want to understand how they change over time, meaning their derivatives, y prime of t, y double prime of t, and so forth. However, these problems are often too hard to solve exactly, especially when y of t is governed by a differential equation. So what do? We'll need to discretize the problem, meaning break it down into a finite number of points. Here's how. We'll choose n equally spaced points on the interval from A to B. Here we have A and B. The spacing between 2 points would be E equals B minus A over n minus 1. So here we have E for the spacing in our illustration. Let's call this point here Tj. And Tj is the jth point in the discretized version of the interval. And T sub j equals to A plus j times E. Assume that our problem involves a function y of t and its derivative, y prime of t, for t in the interval ab. To be a good approximation of the reality, we want to choose a very big number, like 1,000 for n. Let's look at a simplified example of a equals 0, b equals 1, and n is 5. Now we can calculate e equals 1 minus 0 divided by 4 equals a quarter, and thus we can figure out t0 equals 0 plus 0 times a quarter equals 0. t1 is 0.25, t2 is 0.5, t3 is 0.75, t4 is 1. Now we can work with y0 as function of y of t0, y1 as function of y of t1, up until yn minus 1 as function of y of tn minus 1. Then, for the derivatives of y, we recall the trapezoidal rule for approximating integrals. Let's say we have this integral right here. The trapezoidal rule formula states that when c and d are close, the integral would be approximately equal to this formula right here. To illustrate this concept, let's look at the graph on the screen. Our horizontal axis is t, and our vertical axis is z. Our focus is the function labeled g of t, represented by the wavy line. We're interested in finding the area beneath this curve, specifically between the vertical line at t equals c and the vertical line at t equals d. This area is exactly what the definite integral from c to d of gt with respect to t represents. To estimate this area, we can use simple geometric shapes. Here we have A as the point on the curve g of t, where t equals c. Its vertical position shows the value of gc. And f is the point on the curve g of t, where t equals d. Its vertical position shows the value of gd. We also choose the point B between d and f, whose vertical position shows the value gc. The upper bound is rectangle formed by E, F, D, and C gives us an overestimate. Its height is gd, the height of point B and f, and its width is d minus c. Its area is d minus c times g of d. Crucially for this explanation, let's assume c and d are very close to each other. This makes our approximations very good because the curve doesn't change much over such a small interval. For lower bound, imagine a rectangle, ABDC, with its base from c to d on the t-axis and its height equal to gc, which is the height of point A. Then its area is d minus c multiplied by gc. This rectangle represents a lower estimate for the area under the curve. So, the true area under the curve is bounded between the area of the lower rectangle, using GC, and the upper rectangle, EFDC, using GD. This clever method of bounding areas was used by Archimedes over 2,000 years ago. However, we can get an even better approximation by combining these two ideas. The trapezoidal rule uses instead the average of the areas of the two rectangular bounds we just discussed. Its formula is d minus c multiplied by gc plus gd divided by 2. This is precisely the area of the trapezoid AFDC. Now, let's look at an example to see how incredibly accurate the trapezoidal rule can be when the interval is small. We want to compute the integral of e to the power of t from 0 to 0.0001. Here, our function g of t is e to the power of t, our starting point c is 0, and our ending point d is 0.0001. Using the trapezoidal rule, the approximation for this integral is 0.0001 multiplied by e to the power of 0 plus e to the power of 0.0001, all divided by 2. If you calculate that out, it comes out to be approximately 0.00010005. Now, let's find the exact answer for this integral. The integral of e to the power of t is simply e to the power of t, so the correct answer is e to the power of 0.0001 minus e to the power of 0. This also calculates to approximately 0.0000100005. Next, we will shift our focus to applying these concepts or similar mathematical tools to a couple of explicit examples. Our first example is drawn from a lecture note by MIT OpenCourseware. You can find this material by following the link provided in the description below. Within this document, we'll be looking specifically at example 4.4. Before we dive into the robot, let's briefly recall some fundamental facts about trigonometry and Cartesian geometry. First, remember that any point in a two-dimensional space, let's call it point P, can be uniquely identified by its Cartesian coordinates, an x-coordinate, x sub p, and a y-coordinate, y sub p. Second, if we know the length r from the origin to point P and the angle alpha between the line segment OP and the positive x-axis, we can also uniquely determine those same x and y coordinates. Now, let's apply this to our problem. Our question is about how to precisely position the two legs of a doggy robot so that its main body is in a specific predetermined position in space. The robot's body position is defined by two key pieces of information: the coordinates x sub b, y sub b of a central point B, the orientation angle, phi sub b, which is the angle between the horizontal line AC, the bottom of the dog's body, and the x-axis. Note that A and C are the two endpoints of the bottom of the dog's body, and point B is the exact midpoint of AC. Therefore, the body length is 2L, so AB equals BC equals L. Let's focus on the front leg. It's composed of two connected sections, which we call link 1 and link 2. A critical constraint for the robot is that the very end of link 2 must be on the ground, meaning it must touch the x-axis. Therefore, the front leg is determined if we know the two angles. Angle theta 1, which is the angle between link 1 and the YB axis, an axis defined by the robot's body. And similarly, angle theta 2, which is the angle between link 2 and the YB axis. These two angles, theta 1 and theta 2, are uniquely determined if we know the position, that is, the coordinates x sub a, y sub a, of point A. Similarly, the coordinates x sub c, y sub c, of point C will determine the two angles theta 3 and theta 4, and thus precisely define the position of the hind leg. Now, let's put our knowledge of geometry and the robot's body definition into action, starting with step 1. Assume that the length of the links are L1, L2, L3, L4. Our first objective is to find the coordinates of point A, x sub a, y sub a, and point C, x sub c, y sub c, given the central position x sub b, y sub b, and orientation angle phi sub b. This process directly applies Cartesian coordinate principles combined with trigonometry. Recall this is the Cartesian coordinate. Let's look at point A's coordinate. We'll start with what we know. Point B's x sub b, y sub b. Point A is at a distance L from B along the body's axis, which is oriented at angle phi sub b from the horizontal. To visualize this, imagine a horizontal line passing through point B. Draw a perpendicular line from point A down to that horizontal line, calling the intersection point D. This forms a right triangle BDA. The horizontal distance from B to D is L multiplied by the cosine of phi sub B. Since A is to the right of B, we add this to x sub B. So x sub A equals x sub B plus BD and equals x sub B plus L times cosine of phi B. The vertical distance from D to A is L multiplied by the sine of phi sub B. Now with AD, we can add it to y sub B to find y sub A. Likewise, for point C, its horizontal displacement from B would be minus L multiplied by cosine phi sub B. Its vertical displacement from B would be minus L multiplied by the sine of phi sub B. So x sub C equals x sub B minus L times cosine of phi sub B. Y sub C would be y sub B minus L times sine of phi sub B. With these calculations, we have now finished step 1 and know the coordinates x sub A, y sub A, and x sub C, y sub C. Now we move to step 2, computing angles for the front leg. Here, knowing the coordinates of point A, x sub A, y sub A, which we determined in step 1, our goal is to determine the two angles, theta 1 and theta 2, that precisely define the position of the front leg. The leg has two links, link 1 from A to E and link 2 from E to the ground, point F. We want to figure out where point E and point F are. Let's start with link 1. The angle between link 1 and the vertical axis from B is defined as theta 1. Since the body's overall orientation is phi sub B, the actual angle of link 1 with respect to the y-axis becomes phi sub B plus theta 1. From there, if we look at the geometry of the right triangle AEE1, we can write the coordinates of point E, x sub E, y sub E, in terms of point A's coordinates and link 1's length, L1, as x sub E is equals x sub A plus L1 multiplied by the cosine of phi sub B plus theta 1, and y sub E would be equals to y sub A minus L1 multiplied by the sine of phi sub B plus theta 1. Next, let's look at link 2, which goes from point E to point F. To this end, we need to use the angler with the x-axis instead of with the y-axis. Since the angle between link 2 and the vertical B-frame is theta 2, the angle link 2 makes with the xb axis is 90 degrees minus theta 2. This means the angle between link 2 and the main x-axis is 90 degrees minus theta 2 plus phi sub B. Then from E, we will draw a perpendicular line to the ground and cuts the ground at point F1. Since F1 is on the x-axis, we have the right triangle EFF1. Therefore, y sub F is 0 because point F, the end of link 2, must also be on the ground. This means the y-coordinate of E is equal to the vertical component of link 2. We have point F's coordination as is written on the screen. To summarize, for the front leg, we now have the following system of equations that need to be solved to find theta 1 and theta 2. We can apply a similar process to the hind leg to obtain a similar system of equations. Feel free to pause this video to try and write down your system of equations for the hind leg. It's important to note that, to simplify this explanation, we've assumed the situation visually matches the provided pictures. In reality, the lines could be positioned differently while maintaining the same absolute angle, but these situations can be handled with similar considerations. To demonstrate this more explicitly, we could choose specific values for L, L1, L2, y sub B, and phi sub B. This would allow us to set up and solve the system of equations. And if you need a tool to help you solve the system of equations, NUV Optimization app can help you with this. The above problem, which is simple, does not yet involve derivatives. We next will consider the problem of unpowered reentry of a spacecraft where derivatives are needed. This model is based on physics and aerodynamics and is used to study how a spacecraft returns safely to Earth. Here, the unknowns are functions that depend on time, t, velocity, v, flight path angle, gamma, and altitude, h. This problem is represented by a nonlinear system of ordinary differential equations, or ODEs. For system control, we might ask, for example, if we want the spacecraft's altitude h to be 0, meaning it lands on the Earth's surface when time t equals 1, then what should be the initial choices That is, the values at time t equals 0 for v, gamma, and h. To answer this, as we discussed in the first part of this video, we can discretize the time interval. We divide the total time interval from 0 to 1 into n equal subintervals. Each subinterval will have a length, which we'll call e, equal to 1 divided by n. We then use the trapezoidal rule to transform this continuous system of ODEs into a discrete system of equations. Normally, to get accurate results, we'd use something like n equals 1,000. But to make this example simple, we'll use n equals 2, which gives us just 3 time points. T sub 0 equals 0, T sub 1 equals 0.5, and T sub 2 equals 1. The length of each subinterval e is then 1/2. We then define h sub 0 equals h0, h sub 1 equals h.5, h sub 2 equals h1. H prime sub 0 equals dh dot dt 0, h prime sub 1 equals dh dot dt 0.5, h prime sub 2 equals dh dot dt 1. Similarly, we define corresponding values for gamma, v, and also for rho. It's important to note that rho actually depends on altitude h, so rho sub 0 will be a function of h sub 0, and so on. Now let's look at the equations for h in this discrete system. We can rewrite 3 equations directly from the definition of the derivative. Similarly, you can write the other 2 equations for v and gamma based on their respective differential equations. Now we can add the trapezoidal rule approximations. Note that, as discussed about the trapezoidal rule earlier, we also get extra equations that link the values at different time points, like this one as an example. And more precisely for this particular problem, with n equals 2, we have these 2 extra equations. For this problem, we also have our specific control condition, h sub 2 equals 0, meaning the spacecraft lands at t equals 1. Putting all these equations together, the 3 derivative definitions, the extra equations from the trapezoidal rule for each variable over each subinterval and the control condition, we obtain a complete system of nonlinear equations to solve. We won't write down the entire system explicitly here as it is quite cumbersome, but it should not be difficult to assemble from all the concepts we've discussed. Okay, that concludes our video today. We hope it was helpful and easy to understand. We'll see you in the next video, and as always, at NUV Optimization, we can help you to arrive at a precise model for your problem and solve it.